Okay, like every first chapter of every textbook, you try to answer the question, what is this discipline all about? So this course is applied management science. Did anyone ever hear of the term? I know many of you didn't get the opportunity to have Dr. McElnay, but does anyone remember Frederick Winslow Taylor and what he pioneered? Yes, no, I think you probably had Dr. McElnay now. Remember One Best Way? Remember OBW, One Best Way? Frederick Winslow Taylor said when we have a process or a task, there's an optimal way, there's a best way. And he called that field scientific management. Okay, that's very much what we're doing in this class. This class is called Applied Management. And what we're trying to do is we're trying to adapt the scientific approach that's been used in all chemistry and biology and all these things and apply it to the business world, right? Math is the true source of truth behind many things, and we try to uncover it to manage things more effectively, to make better decisions, to have better inventory levels. So we're really trying to solve problems so that managers can do their job better or make a better decision. Our goal is to recommend the course of action that is expected to yield the best outcome with whatever is available. And we'll talk a lot about with whatever is available, because in the world of business, we only have finite resources. We want to utilize those resources the best we can. Okay, that's our job as managers. So the steps in the process, and I'm not going to go through this in a lot of detail, but the steps in the process. The first thing is we need to analyze the business situation and then build models that kind of emulate them, to represent them. So here's the problem I have. How can I model that mathematically? That's a hard part. Okay, you'll see when you do your group project, that's difficult to do because you're thinking, well, what matters and what doesn't matter? What can I decide? What's holding me back? What am I trying to optimize? What am I not trying to optimize? That's a difficult thing to do. We'll get better at that as we go through this course. The second thing is once we have a model, well, a model is nice, but then we want to solve it. We want to come up with a best forecast, a best way. We want to come up with, the best production mix, whatever it might be. That's important to us. That's why we're doing this modeling. And then the third thing, which I don't spend a whole lot of time on in this class because you guys are all, MBA students and you're usually very good communicators, is we need to then communicate and implement that solution. Okay, so we're going to focus a lot on analyzing a business situation, usually with word problems, right? These cases, model it, and then solve it. And at the beginning of this class, we're going to spend a lot of time solving mathematical models. Now, some of these examples are very old. Okay, a lot of these are very old. But it goes back, this discipline goes back, really came out of World War II. Okay, World War II, you think about it, a huge undertaking. We had to move men and machinery and all these things from here to there and get them there more effectively than the enemy. And there was a field that came out of that called operations research. And that's really was the roots of this. What's the best way to move things from here to there, the most efficient, resources were sparse, all those kind of things. So we use techniques, and you'll see we're going to use these techniques like statistical inference, mathematical programming, which is the first thing we're going to start doing, probabilistic models, and networks and computer sciences. So here are some examples. And some of them, like I said, are old, but they make a lot of sense. Burger King uses linear programming to find how to best blend its cuts of meats to reduce costs. How do we make what part of various things do we use to reduce costs and make sure we adhere to these requirements? Okay, that's linear programming. We'll see that first. American Airlines determine optimal flight schedule. So we'll talk later in this class about shortest path models, like how we get from here to here through the shortest path. A lot of logistics companies, a lot of airline companies use those kind of things. Your GPS is using that. When you put in, I want to go from here to here, it figures out the shortest path, and it's using those models behind the scenes. Okay. We talk about project scheduling techniques. The field of project management, there's a course offered in the MBA program as well on project management. It has really blossomed in the last few years. And there's a lot of mathematical techniques we use there. PERT, program evaluation review technique, CPM, the critical path method. It's a way to quantitatively manage a project. Decision analysis is an approach to take some alternatives, some decision alternatives, and apply some kind of criteria to that decision rather than just making it a political decision or a gut feel or a shot in the dark. We try to put some kind of a framework to it. Queuing, queue is just a waiting line, right? So you think about all the places that have queues. Walmart has queues. Applebee's has queues. Disney World has really done a lot of queuing analysis. Sheetz convenience stores, right? Convenience is in their name, right? So they want to make sure that their queues move very quickly. So they've done all kind of analysis, and they actually outsource this kind of thing at Sheetz, I know, to make sure that they have the right number of servers and they have the right flow of traffic throughout their stores. Disneyland, Disney World, like the fast path thing. There's something called goodwill loss while you're waiting in line, and they try to minimize those kind of things because the one thing people complain about when they go to Disney World is the lines. Okay, so we're going to talk about that. So all those things are all we're really talking about there is why we're going to study this discipline, where it came from, why we're going to study. Okay, so let's talk about a model. What's a model? Someone help me. What's a model? What's a mathematical model? What's a model?
Mathematical representation of reality, something you can manipulate and apply to.
Okay, very good. What we're trying to do with a mathematical model is we're trying to represent reality, right, with the underlying math behind that reality. Yes, if I say, how am I going to figure out my profit? Well, I know I make 10 bucks for product A and I make 20 bucks on product B. So my profit is $10 times the number of product A I sell plus $20 times the number of product B I sell. That's modeling that situation, right? It's a model of that situation. Well, we're going to try to do that in a lot of cases. Okay? In a lot of cases, we're going to try to do that. We're going to try to take a word problem and model it somehow. And I want to talk about, before we go to this, I want to talk about some of the ways we classify models and what we're going to talk about in this class. The first type of models, the first way we can classify models is by their purpose. The first type of models we're talking about is optimization models. Optimization models are trying to come up with an optimal method of doing something. Okay, what's the one best way? That's what optimization models are all about. How much of product A and product B should I produce to maximize my profit? How much of my money should I invest in this versus this to minimize my risk, right? The best way of doing something. That's what optimization models are about. The other type of models that we'll study in this class are prediction models. Can we mathematically look at what happened in the past to predict what's going to happen in the future, right? A lot of times, past performance is a good indicator of what's going to happen in the future. It's called a time series forecast. Not always, but usually it's generally good, right? Usually it's a good predictor. So those are called prediction models, predictive models. And we're going to study those a little bit later in the class. We're going to start with optimization models. The second way, so we can classify by their purpose, optimize something or predict something. We can also classify them about the certainty of the data in the model. Okay, the certainty of the data in the model. Sometimes we have deterministic models. Deterministic models means I know for sure what that variable is. Let's say I know for sure I make $10 for every product A I sell, and I know for sure I make $20 on every product B I sell. Okay, those are called deterministic models because I know those things with certainty, or at least I assume I know them with certainty. I could be wrong, but I assume I know them with certainty. But sometimes models aren't that simple. If I asked you, how long, who lives the furthest away? Who lives the furthest away? Where do you live? What's that?
Jackson, Mississippi.
All right, so do you ever drive from Laredo to Jackson? Okay, good.
Monday.
What's that?
Monday.
Monday, you're doing that? Okay. All right. So how long is it going to take you to drive to Jackson, Mississippi, Peter, from St. Francis?
I think it's around 19. But
Okay.
Could be.
I like that. Okay. He didn't say 19. Is it 19 hours every time you do it? Okay, it's not, right? You don't know it for certain. So, Peter, what's the best time you ever made it to Jackson?
Well, I've only done straight shot twice.
Okay.
Because I'd just go to Atlanta and then stay at my buddy's house. And
Okay.
Drive the remainder. So, actually, honestly, it's just better not to time it. So I don't
Alright.
really have an answer. You know, just because
Okay.
I don't really do the countdown.
Well, let's say you average 19 hours. If you made that trip like 100 times, we average 19 hours. But there's some times when maybe you made wicked good time. You know, maybe it only took you 17 hours. Or maybe sometimes you made, awful time and it took you 25 hours. So that variable, how long it's going to take Peter to get to Jackson, Mississippi, is not deterministic, right? It follows a probability model. Most likely, it's around 19 hours, but there's a chance that you're going to get there in 25, or there's a chance you're going to get there in 17, right? So that variable isn't determined, it follows a probability distribution. Does that make sense? So some models use a probability distribution. And in fact, where we're going to pull those out is when we start talking about project management models, right? When I ask you how long is it going to take you to do something, you throw something out, but it's not normally exactly 5 days or exactly 5 weeks. It could be 5 weeks plus or minus a week. So there's some probability associated with that, right? So we'll start pulling those things out a little bit later. Now, what we're going to talk about, and I'm not going to worry about the team approach here, but I want us to look at an example in your book. Okay, so let's do this now. And I know not all of you have your book, so I'm going to summarize this. This is on page 7 and page 8 of your book. And I'll just summarize this probably better. Okay. This is the business situation. You can read the case if you like, but this is the business situation we're presenting. We work for New Office Furniture. And we are scheduling our production run for, let's say, the month of February. Okay. We make 3 products. We make desks, we make chairs, and we make molded steel, which is kind of a byproduct of our stuff. We can sell it though. Okay, we make desks, we make chairs, and we make molded steel. So what we're trying to do, we know we make every desk we sell $50. Every chair we sell, $30. Every pound of molded steel we sell or produce, we make $6. And we're assuming we sell everything we produce here. Okay, we're assuming it's a great market for these products. We also know that the raw material required, which is this metal, takes 7 pounds of molded steel to make a desk, 3 pounds of molded steel to make a chair, and 1.5 pounds molded steel, or steel to make molded steel, and we have 2,000 pounds of this available. So my boss came to me and she said, how many of each product should we produce next month? Okay. What would you do? You could just wing it and make 100 of these, 20 of these, 10 of these, right? Gordon?
Ask how many of each product do we sell?
Okay. Well, we're producing these things in lead time before we even have the orders. We want to have them on hand. So you're right. I mean, that is one thing we could do, and sometimes just in time is the way the companies work. They don't build it until you order it. But these things take us time to build, so we're producing them in lead time. You know what I mean? We want to produce. So what do we do? Go ahead.
Just find out what our fixed costs and what our variable costs are over time,
Okay.
and see what our optimal number is then.
Fixed cost. Okay, so we have fixed cost, obviously, right? And we have variable cost, and that's kind of where we probably came up with those profit coefficients, right? 50 for the desk, 30 for the chair, and 6 pounds. But what we're trying to, that's bigger than what we're asking here. We're just trying to figure out how many of each should we make. Give me an approach. It doesn't have to be the right approach. Just give me an approach. What would you do? Go ahead, Peter.
I guess, what about look into the demand for the products?
Yeah, we're saying everything's demanded. There's demand for everything here. We produce it, they will buy it. It's good. It's a good situation to be in, Peter. Is it Caleb, right?
Yeah, I was just gonna say, depending on pairing between the desk and the chair, you probably wanna lean more towards the desk, since you're assuming that the market's good, and that's your highest profit.
Okay, I like that, okay? So he said, and it's kind of what we call a heuristic model, okay? It's kind of what we call a rule of thumb, right? You said, well, let's just look at it and let's build the product that's the most profitable until what happens, Caleb? Until we run out of pounds of mold steel, right? So we make all the chairs, make all the desks. But I'm not sure, I know this is the highest profit, but it also used the most resources, right? So I'm not sure that's the best way to go. Okay, very good. That's another approach we can use. Okay, trial and error. We can just kind of see, like start up making 0, 0, 0 of everything, and then maybe 1, 1, 1 of everything, and see what it nets out to be. And that's why we're going to use spreadsheets, because spreadsheets can do trial and error a lot faster than me and you, right? They're very good at what-if analysis. So that's another great approach. All those approaches are great. Okay, they're all fantastic, and I think maybe with some effort we could all get there. But we're going to learn to apply, and we're going to learn that this evening, something called linear programming to this. And this is a classic type of mathematical model called a constrained optimization model. Okay? A constrained optimization model. The constrained part is I only have so much of something. What do I only have so much of here? Okay? I only have raw materials. I only have so much raw material. What do you think I'm trying to optimize here? I'm trying to optimize profit. Very good. Okay. And there's something in the case that's not on this slide, but it also has a requirement that we actually do have a contract that we have to produce 100 desks, and we also, and it's not on the slide, but we also only have 500 cushions for our chairs. What do those sound like to you? We have to produce 100 desks, and we only have 500 cushions for our chairs. Of that constrained optimization models, what are those two things I just mentioned? Yes?
You have to obviously make more of one than the other, so therefore that might suggest that there's better investment in the shares than there is in this.
Okay. And really both of those things are constraining us. Okay, so what we want to do now is we want to make this a mathematical model, we want to solve it, and we want to tell someone about the best way to do it. We're going to do that, but we're not going to do that until after break. Okay, but during break, it's going to be a working break, I'm going to hand out a little handout here. And this isn't graded, this is kind of for funsies, I guess. 1, 2, 3, 4. You guys can work together. What I want you to do is I want you to come up with solutions for these 3 problems. However you like. Whatever approach you would like to use. Go ahead, work together. It's 7:25. Oh, by the way, I forgot to talk about this, but I think it's standard practice to move these classes to 6 o'clock if no one has any conflicts. So if you do have a conflict, come up to me during break quietly, because I don't want you to have to be the person to put up your hand and say I have a conflict. So, but if no one has any conflicts, we'll move this class to 6 p.m. Next week. Okay, but if someone has a conflict, we'll just stick it at 6:30. So no big deal to me. Okay, but it's 7:25 right now. Let's take 15 minutes. So we'll come back at 7:40. And while we do that, while you take your break in the bathrooms, you guys, I think all know, but the bathrooms are down this way to the right, so the vending machines. But we'll go over that as well. And then we'll come back and we'll fix new office furniture as well. Okay? Okay, so how'd it go? Let's take these one at a time and see what solutions we might have come up with. So the first one says I have 13 coins in my pocket, can be any U.S. coins, that total $1.19. What are the coins? Then we have a solution to this. Adam? Well, so let me write down Adam. Let's see. So we have pennies, nickels, dimes, quarters, 50-cent pieces, and dollars, I believe. Okay, so what do you have, Adam?
9 pennies, 1 dime, 2 quarters, and 1 50-cent piece.
Okay, so that's got it. Okay, so that's a solution. Go ahead, Jordan.
2 50-cent pieces,
Okay.
9 pennies,
Okay.
and 2 nickels.
All right, that looks good. Anyone else? Diane?
3 quarters, 4 pennies, 4 nickels, and 2 dimes.
There's a handful of solutions to this, right? Okay, so a couple things I want to show you is that the same thing is true in this class. There's going to be problems that we have that have multiple solutions. Okay, multiple solutions to the same problem, like alternatives we call this, right? The second thing, how did you solve this? How did you solve this? What process did you go through? 3 of you solved it different ways. Sir?
Trial and error in Excel.
Okay, you went through Excel, used trial and error. And trial and error is a valid problem solution technique. Okay, and it's actually used behind the scenes in a lot of programming, like the simplex method that Solver uses. It's basically trial and error. Was there anything, though, that helped you solve it with trial and error? Caleb?
I mean, I don't know about as far as trial and error, but right off the bat, you pretty much make it a dime, because you know you need at least 4 pennies. So I kind of went from there.
Okay, one of the things that we know right off the bat, and I think you saw that, is it ended in 19 cents, right? So you knew that the penny field had to be what, either 9 or 4. So that helped, right? That helped that we held, you know, this has to be 9 or 4. That was a starting point, yes? And a lot of times we have these kind of starting points. We have, you know, let's take this off the equation. Let's say this is 4. Let's hold it, you know, it makes things easier if we reduce the number of variables. And we'll do that in the world of management science, okay? How about number 2? A farmer has been given 100 feet of fence to use for his new herd of sheep. What dimensions should the rectangular fence have to maximize the grazing area for the sheep? Note area is equal length times width. So I have 100 feet of fence. I want to maximize the grazing area for this sheep. And I'll let them out here. What is the dimensions that will maximize the area? Anyone? Adam?
Doesn't matter.
Doesn't matter. It does. Yeah. It does. You don't care about your sheep?
They'll figure it out.
I'll figure it out. Your sheep? It matters, yeah. It does. You'll have different areas depending on. It will. We'll see. Go ahead.
I said 22 by 28.
Okay. Why'd you come up with that?
Just trial and error.
Okay. That's pretty good. It's not the best, though. What's the best dimension? No one? No?
24 and a half by 25 and a half.
All right. I think the fact that I use rectangle probably threw a lot of you, right? But a square is just a special rectangle, right? The way to maximize this is to make it square, 25 by 25 or 24 and a half by, you know, that's I guess as close as a square without being a square as you can really get. But if we look at this, you know, if we do it by trial and error in Solver, you know, we can start with, hey, we only have 100 feet, so 49 by 1, you know, and it'd be 49, 49, 1, 1, only gives us 49 square feet. But, you know, if we go you know, we know this has to add to 100 feet, and we go down, it looks like 25 by 25. which is a square, gives us 625 square feet. That's clearly the best. Now, does anyone solve that immediately without even doing the trial and error? Someone just said, it's, hey, the square is the best. No. Now, someone just know that. Okay, the square is the maximum. That's the way to maximize area when you have, maybe the farmer knew that, right? I think farmers do know that. So they do those kind of things. That's called a rule of thumb or heuristic method. And sometimes we use heuristic or rule of thumb method. That's just the best way, right? We know that. That's been passed on from person to person. No need to do the math, okay? And square does maximize area. So let's look at number 3. Okay, let's look at number 3. Number 3 is another agricultural example. So another farmer produces corn and barley. The seeds for the corn cost $100 per acre to plant, and the seeds for the barley cost $50 per acre to plant. The farmer has 80 acres of land and $5,000 to spend on seeds. The money is a government subsidy, so he has to apply it towards the corn and or barley will be given back to the government. We don't want to do that. Corn yields a profit of $80 per acre, and barley yields a profit of $60 per acre. How much of each should he plant to maximize his profit? Solutions to this. No one? So if you're this farmer, you're stuck. Caleb, go ahead.
I mean, that was, obviously you wanna maximize your barley, so
Okay.
I did 70 acres of barley and 15 of corn just to use up the 5,000.
Okay, so you kind of said, well, it looks like barley is better profit per acre, so I want to maximize that. So you went, what, 70 and 15, you said?
70, 15, yeah.
70 and 15.
It's like 5,400 profit.
The only thing 70 and 15, how many acres is that? So you got an extra 5 acres in there. So maybe 70 and 10, okay? That's not the best way. Jordan? But it's a good approach.
I used $4,900 on barley.
Okay. What was your mix?
So I didn't do it by acre, I just did of money.
Yeah.
So $4,900, I took it divided by $50 per acre.
Uh-huh.
That gave me 98. I took that times.
Where are you getting the $4,900?
Oh, because it says we have $5,000 to spend on seeds.
Okay. So why'd you pick 4,900 then?
I must have been wrong. Yeah.
That's all right.
I think I might have did it wrong.
What'd you get for your solution, Jordan?
I came up with $5,980.
Okay.
But I
All
might,
right.
I might have done it wrong.
Yeah, that a little higher than I think we can expect here. Anyone else come up with anything?
Yeah, I did.
Anyone use a spreadsheet to do this, like trial and error? Well, let's use a spreadsheet to do it. And I have a spreadsheet prepared, so you don't have to watch me do it. This is like going to the cooked item in a cooking show. But we can just start with trial and error. So I went 50 of corn. That means the most barley we can plant is 30. I know the cost is $6,500 for the seeds. So what about that option? Is that an option? No, because we spend too much money on seeds. The profit's $5,800. So we keep going down and down and down and down and down until this violates our spending, this violates our spending, this violates our spending. Until we come down, we say, all right, there is 20 acres of corn and 60 acres of barley. Is 80 acres of land, right? We want to use all our land. And it costs us $5,000 in seeds and $5,200. All these are no good solutions, right? These all are no good. Why? We use more money than we have, right? All these are good solutions because we use less than 80 acres or less, and we use less than $5,000. But what's the best solution? Well, the one that has the maximum profit, right? The maximum profit, which is 20 and 60. Now, by the time we're done, well, probably even with next week, this will be so simple to you. Okay, this will be like, if I give this to you on the midterm, you'll be like, oh, that's too easy. You'll go into provost, it's too easy. Because that's how easy this is when we look at it mathematically. So let's take a step back and say, all right, trial and error is an approach, but it's still an ugly approach. It took me some time to build that spreadsheet. I had to do some things. But let's look at the model first, okay? This is a constrained optimization model, okay? And it is a classic version of the constrained optimization model called a production mix model. A production mix model says how much of each product should I sell. or build, or make. You know, how much of product A, product B, and product C. And we looked at a constrained optimization model. There are three things we want to identify, and I want to start with those three things. And I know this is going to sound strange, but I want to talk about this in terms of English first, before we talk about math. Okay? So I'm going to skip ahead to the number 2 thing, because I think that's the easiest thing to identify. As this farmer, what am I trying to optimize? What am I trying to get to the best value of? What am I trying to optimize? What's my ultimate goal? What's my one best way? What am I trying to get the highest or get something the lowest? In a word, I want to maximize my profit. Okay, so the second thing we're going to talk about, this is called our objective. Okay, and it's the thing we want to optimize. You know, pick the optimal one. And you're right, Adam. In this case, I'm just going to use English at this point. We want to maximize our profit, right? If we're a rational farmer, we want to get the most money we can get out of our land, right? We want to maximize profit. That's the thing we want to make the highest or the lowest. What's he trying to decide? What does he have control over? What are the things he can decide? What is he deciding right now as a farmer? What can he control? He can't control how much we make for corn or barley. The market does that. He can't control. What can he control?
What, like how he distributes or like what he plants?
Right. He can decide, okay, how much corn to plant and how much barley to plant. Okay, that's the number one thing. What can we decide? Okay, we'll map that up in a second. But that's number one. What can we decide? And the third thing is, if this is all that was existing in this farmer's world, we want to maximize profit, we want to decide how much to plant, we would plant an infinite amount of corn, an infinite amount of barley, and we'd make an infinite amount of money. But that's not real life, right? There's always something constraining us. Remember, constrained optimization model. We've talked about what we ought to optimize. What is constraining us? What is holding us back? Jordan?
The 80 acres.
Okay, that's one thing, right? The things that we have to adhere to is we only have 80 acres. Okay, so we have to plant less than or equal to 80 acres, right, Jordan? What else do we have is holding us back? Very good. You know, a lot of times these are the things that we have. We have only so much money, we only have so much time, we only have so much, you know, labor, we only have so much maybe land, whatever it might be. Okay, those are the things that are holding us back. So what we've done is we've kind of modeled this, we've taken that paragraph and we've modeled it. We've thought about those three things. Number one, what can we decide? Number two, what are we trying to optimize? And number three, what's holding us back? Okay, now let's take it from there and let's put it in math. Okay, let's take it from English and put it in math. Well, I don't know how much corn and barley I'm going to plant. So let's call them a variable. I mean, let's give them a letter. You know what I'm saying? A variable is a letter that can take on a number of values. So I'm going to come up here, and in my decide thing, I'm going to call these decision variables. That's what we're going to call these. What are the variables that I can change? And the variables that I can change are C, is the number of acres of corn to plant, and B is the number of acres of barley to plant. All right, so I kind of mathed up that because it all goes from those variables now. Now, when I talk profit, obviously, yes, I want to maximize profit, but the word profit isn't math at all. So I want to maximize profit, but let's substitute profit with a math version of profit for this problem. How do I figure out, if I plant 1 acre of corn and 1 acre of barley, how much profit do I make? $88 per acre of corn, $60 for barley, 140, right? 2 and 2, 280, yes? So what did you do mathematically to get that? You said, okay, we'll use some product later. I'm going too far. Too smart. Okay. What we did was we said, let's maximize. We'll take $80. What is it? Corn yields a profit. $80 times the number of acres of corn plus 60 times the acres of barley we plant, right? So if it was 1 and 1, it's 80 times 1 plus 60 times 1, 140. If it was 2 and 2, 80 times 2 is 160. 60 times 2 is 120. That's 280, right? So that function models our objective. And guess what we're going to call it? Crazily enough, we're going to call this the objective function. Because that's exactly what it is. It is a function that models our objective. And by the way, when we talk about optimization models, we can usually we're either going to have the word max here to maximize something, or the word min to minimize something. Like often we maximize profit, but there's things we minimize. We minimize time, risk, accidents, hopefully, things like that. Okay. Down here, what do you think we call these things? Remember, it's called a constrained optimization model. What do you think we call the third thing out here in these constrained optimization models? What do you think we call them?
Constraints.
Very good. Constraints. Okay, these are constraints. And when we talk about constraints, the shorthand that we kind of use is S period T period. And it means, it depends what textbook you read, but it means either such that or subject to. But the constraints are things that we have to adhere to. We must adhere to. We must adhere to. The first constraint you guys told me is we have 80 acres to plant. Okay? So what's the function that models how much we planted in terms of C and B? It's pretty easy. We plant 1 and 1 acre, 1 acre of corn and 1 acre of barley. How many acres do we plant total? 2. 2 and 2? 4. So what's the math there? C plus B is less than or equal to 8, right? The number of acres of corn I plant plus the number of acres of barley I plant has to be less than or equal to 8. Makes sense, yes? How about my seed? Less than or equal to 5,000, right? What's that function look like that models how much we spend on seed? And it's the equation I put into Excel. Every acre of corn I plant cost me how much?
100.
So it would be 100 times C. Every acre of barley, 50 times B. If you remember one of the first slides we talked about tonight, we said we want to mathematically model a business situation. Second thing we want to do is we want to solve it. Third thing we want to do is communicate the results. This is step 1. Okay? This is taking, I know it's a farm situation, but a farm is a business. We've taken a business situation and we've modeled it mathematically. This mathematically represents what's happening there. Okay? If I planted 100 acres of corn and 100 acres of barley, hey, this no longer holds true, right? We violate this constraint. This represents the total profit. I'm trying to maximize it. Okay, this represents what happened up there. Now that's, God bless you, that's not terribly useful on its own, right? Unless we can solve the damn thing. Okay, and that's the next step. But before we solve it, let's go back to my new office furniture. Okay, you guys recall new office furniture? Let's go back to new office furniture. And let's go, instead of straight from the English, let's go straight to the math. think of these three things. New office furniture, what can I decide? New office furniture, what am I trying to optimize? And new office furniture, what is holding me back? Okay, and this is the one on page, I think it's 8 and 9 of your book, or 7 and 8 of your book. So let's start with decision variables. What am I trying to decide? And this, by the way, is also a production mix model. We do a lot of these at the beginning because they're supposed to be the easiest. What are our decision variables at new office furniture?
How many desks and chairs are we using?
And what else, Adam?
Molded steel.
Okay, so our decision variables, number of desks to make is D. Well, number of chairs to make is C. And we'll call M the number of pounds of molded steel. I think that makes sense. You could use A, B, and C if you want, X1, X2, X3. It doesn't matter as long as you keep it consistent throughout your model, right? It doesn't matter what you call it. Okay, so that is the thing we can decide, the thing we can control at new office furniture. What am I trying to optimize in this case? Same thing we're trying to maximize or optimize in the corn and barley problem. What are we trying to optimize? Profit, okay? But instead of representing profit as the word profit, we want to represent it mathematically. So in this case, how would we represent a function that represents profit? Every desk I make, how much do I make?
50.
So 50D plus every chair is how much? 30C plus 6M, I think it is, right? 6 pounds of mold, $6 per pound of molded steel. Okay, that's my objective function. My third thing are my constraints. And some of these are up here, but I remember in the book it added 2 others. It said that we only have 500 cushions for our chairs, and we have a contract to provide 100 desks to some vendor. So we have to produce at least 100 desks. So all those things are constraints. So what is one constraint? Give me the constraint that's on the slide. How would we model that? How would we model the constraint for our raw materials in this case? Eric?
D is greater than or equal to 100.
Okay, that tells me that one would be a constraint. Which one is that modeling, Eric? You're right. What is that modeling? That we have to produce 100 desks. That's modeling that contract, right?
Right.
That's saying force D, everything in subject to, we have to adhere to, right? We have to adhere to that. So that's forcing us to have at least 100 desks. Done. That's one of the constraints. What else? What else could we model? The other 2 things that are holding us back are pounds of steel, and also we only have 500 cushions. So what else? So model one of those for me. How about the cushions? They limit the number of chairs we make, right? We only have 500 cushions. The most number of chairs we can make is 500. So we'd have a constraint that says C is less than or equal to 500. 2 things holding us back. What's the third thing holding us back? The steel. How would I model that? How many pounds? Noah, how many pounds do I have?
2,000.
2,000, so I can't go over that. I can go less than that, but I can't go over that, so less than or equal to 2,000. What's the function that represents the amount of molded steel or steel I'm using? Noah?
70 plus 3C plus 1.5M.
Very good. So this whole deal, okay, this word problem, when we mathematically model it, becomes this, okay? Once again, it comes down to these 3 things. What we, as the manager, can decide upon, what can we change? Those are called decision variables. What are we trying to optimize? Make real big or make real small. That's number 2, the objective. And number 3, what's holding me back? What do I have to adhere to? Right? Usually time, money, those things, raw materials, those are the things holding me back. This is modeling that situation. Now, the other thing that we see here, and these constraints I'll talk about a little bit, oftentimes we know we can't produce negative chairs. We can't produce negative desks, right? It's called the non-negativity constraint. Same thing with the corn and barley. We can't plant negative acres of corn. We can't plant negative acres of barley. So a lot of times we include what's called the non-negativity constraint to model that, hey, in real life, you know, these can't be negative numbers, right? You can't plant, it's either 0 or more, yes? That's called the non-negativity constraint. And sometimes we need to build in what's called an integer constraint. An integer constraint means it has to be a counting number. Now, I can tell you we try to avoid using that constraint as much as we can, but the book chose to use it in this case. So they said D and C are integers. We can make half a pound of molded steel, but we can't make a half a desk or a half a chair, right? Either we make 0 chairs or 1 chairs or 2 chairs. No one wants a half a chair, right? So we say D and C are integers. Okay, that's called an integer constraint. Okay, the other names for these constraints are, if it's a greater than or equal to, we call that a lower bound constraint. Obviously, because there's a lower bound on it, it has to be greater than or equal to 100. That's a lower bound. And if it's a less than or equal to constraint, we call that an upper bound constraint because it has an upper bound. Okay, just some terms here. Okay, still not really impressive, right? So what? Now I have something that I don't know the solution to in math form, but I still don't have the solution to it, right? All I've done is taken it from words to math, but I still don't know how to solve it. Well, this is where the second part comes in, okay? And we're gonna introduce it this week, but we're really not gonna do any homework on it until next week. So I'm gonna start talking about solution techniques. Now there's a couple different solution techniques to solve this thing. One of them, which I used to make the students do, which was ugly and time-consuming, and they hated it, was graphically. Okay, I can graph these lines, and I can figure out what the feasible region is, and see which point has the highest profit. I could do that. That's one thing I could do. And the other one that we're going to rely on in this class is we're going to use the spreadsheet package, and we're going to use Microsoft Excel. Okay, but we're not just going to use the plain Jane, Microsoft Excel. We're going to use a special aspect of Microsoft Excel. So if you have a laptop today, you can get it out. If you don't, just follow along. And we're going to do this again next week, so you'll be fine. So hey, we're going to meet at 6 next week. Okay, no one said anything. So speak now or forever hold your peace. So we'll meet at 6 next Tuesday. Okay. All right, so I'm just going to open a blank workbook. So open a blank workbook. It doesn't matter if it's 2007, 2010, even 2003 will work. Excuse me. Okay, what I'd like to do is let's do the corn and barley guy. Okay, let's solve that. So in column in C1, I'm just going to put a label, and I'm going to label corn. And then in D1, I'm going to put the label barley. Barley. Might as well center that. And those are just labels. We don't need them, but they help add clarity to our model. So what I'm going to try to do is I'm going to take what's on the board and put it in Excel. So my C and my B are really in C2 and D2. So I'm just going to start by like preloading this. I'm going to assume I'm going to start making 1 acre of corn and 1 acre of barley. I know that's not going to be the final solution, but let's throw it out there. Let's throw 1 acre of corn and 1 acre of barley in there. So in C2 and D2, I'm going to put 1 and 1. Okay, does that make sense? So really what I've represented so far in Excel is my variables. None. Okay, that's all I've represented. I'm going to skip a line, and I'm going to come to B4, and I'm going to write the word max. And it's just a label, so if it's not right, no big deal. Just write the word max. Okay. And when I wrote this, and I didn't do a good job with this one, but I did a better job with this one, I tried to keep things aligned. And there's a reason for that. See, all the D's are together, all the C's are together, all the M's are, I did a terrible job there. But when we emulate it with Excel, we're also going to use those coefficients, okay? So in C4, I want to put the coefficient for corn. The coefficient, if you remember, the coefficient is the thing before the variable. And in this case, the coefficient in my profit is 80. So put in 80 there. And my coefficient, I'm going to tab over. My coefficient for barley is 60. Okay, that's all I'm putting in is the coefficients there. Whoops. Now, in E4 is where I want to put some Excel formulas. Okay. I want to put a formula in here that shows me total profit. Okay, what would that formula look like? What are we doing up here mathematically? We're saying take 80 times C, where C is the number of acres of corn, plus 60 times B, which is the number of acres of barley, right? So where's 80 at? What cell is 80 live in right now? Okay, C4. So I'm going to put C4, which is 80. What's times in Excel? You remember we start all formulas with Excel, with equal? What's times in Excel? Okay, yep, star or asterisk. So C4 times, where are the number of acres of corn that I'm currently planting? Where's that variable live? C2, right? Where column C, so 80 times C2. Basically what we've run in there is this part, and we just modeled this. In Excel formulas, you never put in spaces, so I'm going to put in a plus. Okay, no space there, just C4 times C2 plus, where's my barley? The 60 is in D4. My number of acres of barley is in D2. And now I hit enter. Okay, put that formula in there. If I change this to 10 and 10, you'll see it automatically changes my profit, right? Or if I change it to 5 and 5. So you can imagine I could do a what if analysis. You know, what if I might plant boom, 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 and it will automatically update everything. Now, if I want to go back in and change that formula, I can either double click on it. You see it puts it in edit mode now, down on the bottom left, and I can change whatever I like. Or I could go back to that cell and hit the F2 function key. That puts it into edit mode as well. Okay, a couple ways to get there. There's an easier way to enter that formula, but we'll talk about that next week. We'll do things the long way this week. So far, I've taken this mathematical model and I put step 1 in Excel, and I put step 2 in Excel. That's it. Okay. What else do we need to put in here then? We need to tell Excel about our constraints. Okay. I'm going to skip a line for clarity, and I'm gonna put ST in A6. And I'm gonna put profit in F5, F4, just so, it's just a label, but. Okay, and in B6, I'm gonna put a label for my first constraint, and let's just use one word, and we'll say this is acreage. Okay, because we're gonna model this acreage constraint. What's the coefficient here and the coefficient here? It's implied, they're not written, but what's the coefficient in both those places? It's 1, right? So I'm gonna put a 1 and a 1 here. Okay. Now in E6, I want to live a formula that tells me how many acres I planted. So, and I know there's easier ways to do this, but we're going to do it the long way this week. How do I get a formula that represents the number of acres I've planted? Anyone?
C6 plus D6.
Okay, I'm going to say C6, which is the coefficient, times C2, which is the number of acres, my decision variable, plus D6 times D2. And I'm going to hit enter. And now when I change these, you'll see 10 and 10. Everything changes below. And what do we say about the acreage? We said it has to be less than or equal to. So I'm going to put less than or equal to in F6. And then I'm going to tab over. I'm going to put 80 all alone in G6. All right, so I've captured that first constraint. Let's go to row 7. Let's put in B7, let's put in seed, because that's the constraint we're modeling here. What's the coefficient for corn? How much does each acre of corn cost me in seed money? 100. Barley cost me 50. And if I want to figure out the total amount of seed money I spent, it would be C7 times C2 plus D7 times D2. Oops. Times D2. And that has to be less than or equal to 5,000. Now I still haven't solved this, right? I still have not solved this. All I've done is taken something from the whiteboard and put it in Excel, which is an improvement because now I can say, oh, what if we do 110 acres? Well, I make $8,600 profit, but automatically we know that's not feasible because what? I use too much acreage and I use too much money, right? So maybe I play around and I say, all right, 20 and 30. Okay, well, let's see, I used 50 acres. I still have money left, so maybe go up a little bit higher. Maybe do 30 and 30. I still have some acreage left, still have some money left. Maybe go 40. And I'm going over my seed balance now, right? So that's no good. So I could do what-if analysis, but it might take me a long time, right? Because I'm human and I'm not a machine, and I don't have the capabilities of a computer. So what we're going to invoke is something that will solve this for us. Okay. Now, there is functionality that comes with Excel that is typically not turned on because 99% of people don't use it. Well, welcome to the 1%. We are going to turn on some functionality tonight that most people never see. So I want to show you how to do that. Right now, if you go to Data, okay, most of you probably don't have analysis solver. Does anyone have analysis solver? Someone might. Do you have it, Adam? You probably turn it on in stats, right? Okay, but most won't. So we're going to turn that on. So this is a one-time thing. We just have to turn it on once. It takes some memory, and that's why it's turned off when it starts. I want you to go to the File button, or if you're in 2010, you go to the Office button. With that, whatever you have, you know, the File button or the Office button. You guys with me? Okay. And I want you to go to Options. And you should come up with something that looks like this dialog. In this dialog, there's a button here or a selection says Add-ins. I want you to click on Add-ins. Add-ins are, as I said earlier, they are advanced functionality that comes with Excel that most people don't use, so they're turned off. But we're just going to turn on some of our advanced functionality because we're going to use it in this class. There's like a Euro currency tool, there's things for statistics. What we want to turn on is if we go down to this button that says Go, click on Go. And you should be presented with a series of check boxes. And turn on Solver Add-in. Just check it, and then click OK. Now, if you have a pirated copy of Excel, you may have issues at this point, but if you have a legal copy of Excel, you'll be all right. Okay. Everyone able to do that? So now to validate that, under Data, under your Data tab, go to the right, and you should see, under an analysis group, you should see Solver. Do you guys see Solver? Yes? No? Okay. Under some older versions of Excel, it might be under, there's a option called Tools, Add-ins. You might see it over there, Tools, Solver. But I think most people have 2010 or 2013 now. Guess what Solver does? Solves. Very good. Doesn't everyone need a little solver in their life? So we're going to solve this using Excel Solver. So what I want you to do, now that we have this model built, and this gets a little hairy, and don't fret if it's too much this week, because we're going to do more of this next week. Okay, I'm going to go slow through this, but let's invoke Solver. So I want you to go to Solver. It's going to bring up a new dialog. And basically what it says is, hey, I know you built this model, but I need you to tell me Solver, about these three things and where they're at in your model. Where do they live in your model? So the first thing it wants to know is, if I had one cell that represented my objective, what is that one cell? What is the one cell in my model that represents the thing I'm trying to optimize? What one cell represents the thing I'm trying to optimize? Very good. My profit, which is E4. So, a couple ways I can get E4 in there. The first thing I can do, easiest way, if I click on the little spreadsheet selector next to it, and then I go and I click on E4. You see it put E4 up here. And then I click on the little drop down window shade, and I put E4 in there. You could also, if you want to use the keyboard, you could just delete it out, put in E4. Does the same thing. I tend to like to use the mouse, so hit that, E4, close the window, E4 is in there. Okay. The next thing is, there's a little option button here. What are we trying to do to E4? Maximize it or minimize it? So that's how we tell Excel what we want it to do with it. Now, Excel says, all right, I'll make that as big as I can make it. But you have to tell me, what am I allowed to change? What am I allowed to decide on to make that big? What, as the farmer, are we allowed to change, and hence we're gonna let Excel change. What cells, as the farmer, are we trying to decide, and we're allowed to change? Very good, C2 and D2. So, I'm gonna use that little spreadsheet. I'm gonna click on it. And I'm gonna click and highlight, left click and drag C2 and D2. And you see, it puts it in as a range. It says C2 colon D2. That means, hey, that's the range. C2, the colon means like through, right? Start at C2 through D2. And I hit the drop down. Okay. So we've told it about 2 and then 1. So we've told it about what we're trying to optimize and what we can decide to optimize that. Now this one's a little bit trickier, okay? Now we need to tell it about the constraints, each constraint. Because if I just solve it now, it's gonna say plant an infinite amount of corn, infinite amount of barley, I've just made you an infinite amount of money. But that's not real life, right? We can't. So we have to tell it about the things that are holding us back. So on the constraint area, I'm going to click add because I need to add a constraint. So I'm going to click add. And it brings up a little separate dialog. Okay. What one cell represents the total amount of acreage I've used? Not how much I have, but how much I've used in this current model. What cell represents the total amount of acreage I've used? If I plant 44 acres of corn, 30 acres of barley, how much acreage did I use? 74 acres, which is in what, Jordan? E6. E6, very good. So in the left-hand side, I'm going to say, hey, whatever is in, I'm going to click on that little spreadsheet. Whatever is in E6, close that spreadsheet. I'm going to get E6 in there on that left-hand side. Has to be less than or equal to. We don't have to change that. It's already less than or equal to. I'm going to click in this right-hand box. That has to be less than or equal to what? What's on the right-hand side of that constraint? Has to be less than or equal to what? 80, and instead of writing in 80, I could write in 80, but if I can, I like to use cell references, so G6. So I have E6 less than or equal to equal G6, which is just the same as G6. And then I'm going to click add. And this, I don't like the way Excel Solver works here, but it just doesn't really give you a message that says, okay, that was good. It just kind of blanks things out. And you're like, what the hell happened? But it did enter it into our model. So just bear with me, okay? So it's there, I promise you. We also want to tell it about the constraint for our seed money. So where is the amount of seed money we used? Very good. So I'm going to say E7 in the left-hand box is less than or equal to, in the right-hand box, I'm going to tell it 5,000. So I'm going to click on 5,000. And then I'm going to click on add. And once again, it goes away, and you're like, what happened? Okay, well, at this point, just click on cancel. And you'll see it added in those constraints for me. When I clicked OK, it put them in there. See, it says E6. E6 is less than or equal to G6, and E7 is less than or equal to G7. Make unconstrained variables non-negative. What we're doing there is saying corn and barley has to be greater than or equal to 0. That checkbox is doing the non-negativity constraint for us. And then under select a solving method, choose simplex LP. Okay, simplex LP uses something called the simplex method to solve this, which is basically trial and error done at lightning speed, computer speed instead of human speed. Okay. The moment of truth. Click the solve button. If you set up everything correctly, it should say, hey, solver found a solution. All constraints and optimality conditions are satisfied. Do you want to keep the solution? I'm going to say okay. And it came to me and said, the one best way is to plant 20 acres of corn and 60 acres of barley. I will make $5,200. I will use all my acreage and all my seed money. Okay, that is the solution for the farmer. So we went, and that is the one best way. Okay, that is it. Uses all his acreage, all his seed money, and gets him the most money. Now the beautiful thing about it being in Excel is we can do what-if analysis quite easily. If the farmer, I don't know, gets an extra 10 acres off his sister that lives next door, I can say, well, I have another 10 acres. I want to see what that does. All I have to do is change this 80 to 90, go to solver again, and all those values are still in there and all referenced correctly, and resolve, and it says, hey, now the one best solution is to plant 10 acres of corn and 90 acres or 80 acres of barley, and you're going to make $5,600. And if anything changed, if these profit coefficients changed, if for some reason we knew corn was going to be, wicked profitable, maybe, I don't know, $200 an acre profitable because there's a corn drought somewhere in the world, we could put 200 there, and we resolve, and it says, hey, now, given that situation, the hell with it, use 50 acres of corn, and the heck with the barley. We know we have 30 acres that we're not using, but we used all our seed money, so that's the best way to go. Okay. So all these things, these constrained optimization model, they're based on three things. There's something that we want to optimize. There's something we want to make the best it can be, the one best way. Maximize something or minimize something. There's things that we can change. Those are our decision variables. And there's things we can't change. There's things we have to live by. There are things in our environment that we'd have to adhere to, right? Those are called our constraints. That's what management is. It's trying to make the best of limited resources, right? Trying to make the best decisions from limited resources. This is a way to take business situations, to model them, and then to solve them. And based on that solution, you can make a recommendation on how we might implement this. Okay. Now, I know this is class 1, and I know I don't want to go too far in class 1. Sometimes I feel like I do, but we're going to spend some time on this. So if today was like, over your head, I don't want you to sweat it at this point. We do spend a lot of time on these models. We'll spend a lot more time doing this in Solver. Some of you may be very proficient in Excel, some not so proficient. I think we go at a pace that we can handle all levels of Excel capabilities. We'll go step by step for the first few. This is not what the homework will be like. Okay, the homework, you're not going to have to solve these for this week. We'll start doing those for the homework for next week. What the homework will be like is I want you to start thinking about these three things. What we can optimize, what we're deciding, and what our constraints are. And after you take this course, you actually start thinking about that in a lot of ways. Okay, I think I do anyways. Like, you can apply it to a lot of things. Like, hey, I want to have as much fun as I can, but I only have so much money, right? What do I do? Where do I go on vacation? Think about it. A lot of things can use that model. Not all can be mathematical, but a lot of things can use this model. So we are going to uncover a bunch of different models. This is the first one. This is the first one that's introduced. It's called a constrained optimization model. What we're doing here is called linear programming, okay? Because we're going to solve this solving it with lines and something called the simplex method behind the scenes. We solve with graphs as well, but we're going to do it with Excel Solver. Questions on that? Was that most people able to get that to work on their Excel tonight? That's good. Okay, that's very good. What I would like you to do for homework for next week then, and if you struggle with the homework, the solutions are right here under chapter 1. but let me look at the homework. And this is on pages 40 to 43 of your text. And I would like you to do number 3, number 5, number 6. Now, number 6 is going to be probably the most difficult one for you. Number 6 is something called a model shell. A model shell is everything's a variable. You know, like in here, we said we make 80 acres for every acre of corn we plant and 60 for every acre of barley. Well, if instead of saying 80 and 60, we said we make X dollars for every acre of corn and Z dollars for every acre of barley, everything's a variable in a model shell. So it's not hard, but it's very abstract because everything's going to be represented with variables, with characters, okay? So don't sweat it if you have difficulty with number 6. Number 7, I would like you to do. And there are, in this book, there are exercises on Excel skills, okay? And we're going to do, more Excel next week and utilize and learn some new functions. And we didn't do anything with like static references or copy and paste, and we'll learn all that next week and F4 and all those good things. But if you're not good with Excel, 11 through 19 in the back of your book kind of has some Excel exercises that you can do. And in the back of chapter 1, for the end of chapter 1, there's a little chapter appendix that has, doing things in Excel. The formula we're going to use a lot in this class is something called sum product. It's a pretty easy formula, but there's something in there about sum product that might behoove you to look at that. Okay? 6 o'clock next week. 6 o'clock. All right. I probably won't remind you. Just come at 6 o'clock. Any questions you guys might have? All right. I look forward to the next 13 weeks or so. Nice meeting you all. Please drive home safely. And